Yes, welcome. We will also be talking about the problems the software tinc to make a VPN encounters when trying to send your packets over the internet. And the problems it encounters is not only applicable to tinc, but also to other VPN software or other peer-to-peer applications. So a bit about tinc. It started in September 1997 when there was a new kernel, and it came with a new device, the EtherTap device. And you now know it as the tinc device, maybe. But then I thought, oh, that's nice. What can I do with it? And I wrote a little program that captured the packets from this virtual network device that the EtherTap device created. And you could send it via Netcat or SSH to another computer. And there you could do the reverse. So you could send up a VPN. But it grew and grew. And currently it's a mature daemon that has a number of features. For example, that it connects multiple sites together, not just two endpoints, but any. It routes packets, or it can switch them, so it can work like an Ethernet device or a router. It fully supports IPv6, both on the VPN, but also when tunneling packets over the internet. It has no central server. It does not make a distinction between clients and servers. And the idea is that you configure some endpoints in the VPN, and then tinc will fill in the rest and will create a full mesh network. I will explain that later. Behind the screens, it works this way, very simply put. The daemons connect via TCP, they exchange data. In the kernel. Then there was VPN, which started at the same time as tinc. But these projects are, to my knowledge, dead now. But you all know IPsec and OpenVPN, I think. And another one is Hamachi. It's a closed source, commercial-like. It's kind of a Skype for VPN, which is peer-to-peer and shares many of the features of tinc. But lesser known, but other projects, all open source projects. Here are the GNU Virtual Private Ethernet, which was started as a fork of tinc. Cloud VPN, social VPN, end-to-end. And last year there was a presentation here about virtual distributed Ethernet, which deals with connecting virtual machines together, but actually it shares most of the features of VPN. So, what do you want to do with tinc? Now, we have the internet here, it's the blue cloud, and we have some nodes. These are the black circles. Now, a node can be a single laptop, for example, at a hotel or an airport, or it can be a complete network from a company. And we all want to connect these nodes together into a single VPN. Now, what you have to do, each node has to supply some configuration to tinc, so that each node can make a connection to another node, so that they are all part of the VPN. But it doesn't matter in which way you connect nodes. The topology is up to you. But then tinc will exchange information between nodes about where everybody is, and tinc will create direct connections from each node to every other node. But it uses connectionless UDP for this. This is efficient and it scales well, even if you have 100 or more nodes. But the reality on the internet is not so nice. I've drawn a few red lines here. These red arcs here, for example, are network address translators, which are very common these days. And the problem with those is you can make outgoing connections, but incoming connections fail. And another problem is that some ISPs tend to block certain kinds of traffic. For example, they can block UDP or only allow port 80 communications. And that's the red line here. Now you see that most of the lines, the solid lines from the previous slide, have disappeared. And And some nodes, for example, behind net devices cannot connect directly with each other anymore. You can still go via another path. But more problematic is that if a node connects to another node behind the net, and that's the initial connection it makes, then it does not receive information about where the rest is. So it is completely disconnected from the VPN. Now I will describe most of these problems in some more detail. The problem of NAT is that the source address and port change, and incoming connections are blocked, even if you make an outgoing connection to the same to the other side, because they don't know what the new port is. There are a few solutions. You can route via a third node, but that's inefficient, of course. You can do port forwarding, but the user has to set up on his NAT device, and it's manual work, and maybe your NAT device does not support it, or you cannot, you're not the administrator of that device. There is a protocol called UPnP, which allows you to discover NAT devices on your network. You can find out which ports they map your connections to, and even open up connections. And there is this protocol called Session Traversal Utilities for NAT, or Internet Connectivity Establishments, which are IETF protocols, which allow you to puncture holes through a net. And in some cases, it can allow you to establish direct connections. But this is a complex protocol. And it's also not always possible. Some NAT devices just do not allow any form of direct communication. To put it in pictures, we have two nodes behind the NAT device, and they want to make a direct connection. But the outgoing connection works, but here ends up being blocked by the NAT. The other one tries to connect back, and it also fails. But they can exchange information via a third node. Now, the idea is that the third node knows, because it can see the port and address that the NAT device maps the internal connections to, which port and address the other nodes should use when connecting to the first node. So if both nodes know this information, they can adjust their connection to use the right port to go through the NAT device. Another problem that we encountered is that packets are fragmented on VPNs, because if a packet on your VPN is already the maximum size that your network allows, then you encapsulate it in a new packet, then this will be larger than the original packet, and it will be fragmented by the operating system. Now, this is a bit bad for performance, but more importantly, some ISPs or firewalls block fragments. And so this would block most of your VPN traffic. A solution that we implemented is to determine the path maximum transfer units between nodes. And then when one node wants to send a packet to another node and it has to fragment it, instead the tinc daemon will generate an ICMP fragmentation needed packet, which tells the original sender, hey, your packet is too large, you have to make it smaller. And this is an IP level mechanism, so this should in principle work for all IPv4 and IPv6 traffic. And for other kinds of traffic, which tinc can also support, it will fall back to TCP encapsulation. But the problem is that there's also some firewalls and ISPs that block ICMP packets. Because 10 years ago, you could still crash computers by sending large ping packets. So they decided, oh, block all ICMP. But yeah, the problem is then that when tinc generates ICMP packets and they somehow leave the VPN and go to the internet, this can happen if you have your default gateway on the VPN and have road warriors connect to that via the VPN. Then a host on the internet tries to send packets to the VPN, but these packets are too large to be transferred via the VPN to other nodes. And then tinc generates ICMP packets back. But if the some host behind the internet does not see these ICMP packets, will never adjust the packets that are too large. Now there's another solution, and this is to clamp the MSS field in TCP packets, which is another mechanism which does not use ICMP packets, but just the TCP packets itself. And that will also instruct the other side to reduce the size of the packets. But the limitation here that it's only working for TCP. Now, a few other things we encountered is hosts with frequently changing IP addresses. If you have a cheap ISP, for example, then you can use dynamic DNS services, for example. Or you could have other nodes on the VPN remember and forward known addresses of other nodes. And that's all already implemented in tinc for some years. There are ISPs that only allow certain types of traffic. For example, they only allow web traffic. So you have to encapsulate everything into HTTP or HTTPS. And in some cases, you can use ICMP if it's not blocked, or DNS. tinc does not implement that, but there are some VPN solutions which do allow it. And there are also lots of utilities around which can encapsulate any TCP stream into ICMP or DNS for you. And then there's another difficult problem, ISPs that are dropping or delaying small UDP packets. This is a commercial motivation because voice over IP also looks like small UDP packets. And if they offer telephony services for which you have to pay much more than for your internet connection, then they want to disallow voice over IP and make it difficult for you. The problem is, if you drop packets, then TCP streams inside those tunnels think it's because of congestion, and they will reduce their bandwidth. And for this, it's a really hard problem, and I don't have a solution for this yet. Now, okay, the internet is hostile, but that's probably the reason that you want to set up a VPN in the first place. But how do you trust your nodes? You have to have some form of authentication and authorization. The authentication is proving who you are, and you can do that by using a passport, for example, in real life. It's a document that shows you I am Guus Sleepen. And the nodes on your VPN also should do that. You don't want to allow any node on the VPN. But proving who you are is not the same as saying, okay, you are allowed to use this range of IP addresses on my VPN, or you are allowed to use this much bandwidth on my VPN. And the problem is that these days a lot of authorization is actually authentication. For example, you are allowed to access a web server if your client certificate, which is just a way to authenticate you, is in a list. But that does not, there's not a method of doing proper cryptographic authorization. But two well-known, and that's mostly authentication methods, are the X509 certificates. It's, you know it from HTTPS connections. It's a centralized approach, so there's VeriSign at the top and some other companies, and via a few middlemen which all want to extort money from you, you can get this certificate. But it focuses on identities and websites because it's made for that. So you can only put some information like an LDAP identity, like my organization is called this and I'm from this country, into a certificate and may be limited to a certain URL. OpenPGP keys, I think they're very nice because they have a decentralized approach, but it also has this limitation. It was meant for email, so it is limited to email addresses. So we want something different. We want something that has some of PGP features like decentralized workings, a web of trust that you can build up. But we want more. We want to authorize anything, not just email addresses. We want to add and remove authorizations very quickly. We don't want to go through revocation methods. We want to forbid things as well. And we want to make group decisions so that every node, for example in the VPN, has the same way of allowing or disallowing other nodes. So I created a library for this. It's a lightweight framework to do authorization. You can create many small certificates. For example, let's say somebody said, one of the nodes for VPN, for example, that at a certain time that another node is allowed to access the VPN. And newer certifications just overrule older ones. So you don't have a revocation certificate. No, you have just an updated authorization. And the library makes it very easy to query these stored authorizations. And we do not want just a list of the certificates. No, we just want to know, is this person allowed to go on the VPN? And the library, okay. Anyway, you can find more about the website. And there's a Birds of a Feather session at 5 o'clock.